All right, let's get right into it. In the world of programming, we're always chasing speed. Faster, more efficient, you know the drill. So when a new JavaScript runtime pops up, this one called protoJS, and it claims to be 20 times faster than Node.js, you kind of have to stop and ask, wait, how is that even possible?
And that's the big question we're tackling today. Is this just some clever marketing, or is there something fundamentally different in its DNA that unlocks this kind of insane performance? We're going to peel back the layers and find out exactly what's going on under the hood.
And to be super specific, the official benchmarks land on a speedup of 19.83 times. Let that sink in. That's not just a little faster, that's a generational leap in performance. And numbers this big, well, they just don't happen by accident.
So here's the thing. The secret sauce for protoJS isn't one single trick. It all comes down to three deeply connected secrets baked into its very foundation. A C++ core they call protoCore. And today, we're going to uncover all three.
So welcome to the 20x performance mystery. Our investigation starts not with protoJS itself, but with its heart and soul, protoCore. Because if you understand this core, you'll understand everything. Now, check this out. To really see what's going on, look at where the biggest gains are. Array operations. protoJS gets it done in 44 milliseconds. Node.js, over 1,500. That is a staggering 34 times faster. This isn't just a minor tweak, it's a completely different way of thinking about data. And that right there leads us straight to our first secret.
Okay, secret number one. It's all about how protoCore handles data from the moment it's born. It uses what you could call smarter objects, and this is all built on two really clever concepts. First up, tagged pointers. So in a lot of languages, even a simple little number has to be put on the heap, which is, slow. But protoCore is slick. It uses a few bits of a pointer to tag what kind of data it's holding. So if it's a small integer, it just stores the number directly inside the pointer itself. Think about that. No memory allocation, no garbage collection overhead, just pure raw speed for the most common things you do. The second part of this is immutability. This means once you create something like a string or an array, it can never be changed. Now, I know what you're thinking. Doesn't that mean you have to copy everything all the time? Sounds super inefficient, right? Well, no. And that's where the magic is.
And this shows you exactly how. When you want to add to an immutable string, you don't actually copy all the original characters. You just create a tiny new object that points back to the original parts. It's a technique called structural sharing, and it's the reason those array operations were 34 times faster. You're not lugging huge chunks of data around, you're just rewiring a few tiny pointers. It's brilliant.
Okay, that was just the first piece. Let's build on that and get to secret number two, lock-free state. See, managing data that lots of different threads need to access at the same time is one of the hardest problems in computer science. And protoCore's solution is both simple and totally radical.
The old way of doing things is with locks. One thread locks the data, does its thing, and then unlocks it. But this creates traffic jams, bottlenecks, and the absolute nightmare scenario, a deadlock, where everything just grinds to a halt. protoCore just throws all of that away. It uses a lock-free approach for high concurrency and zero chance of deadlocks. So how does it do that? With this one central component called the mutable root. You can think of it as the one single source of truth for every piece of shared, changeable data in the whole system. Instead of trying to manage locks all over the place, every single change has to go through this one central choke point. And the process for updating it is like this elegant little dance. A thread reads the main pointer, copies the data, and modifies its own private copy. Then it tries to atomically swap its new version in. Now, if another thread got there first, the swap just fails. No big deal. The first thread just grabs the newest data and tries again. No thread ever has to wait for another. It's basically an optimistic race to the finish, and it is incredibly fast. And all of that brings us to the final piece of this puzzle. Secret number three, a blazing fast garbage collector. You know, GCs are famous for causing those awful stop-the-world pauses where your whole application just freezes for a second. Well, protoCore's GC is specifically designed to make those moments practically disappear. And here's where it all starts to click together. Remember the mutable root from our last secret? Well, because all the shared state is in that one single place, the garbage collector doesn't have to go on a scavenger hunt through memory to figure out what's still being used. It just has to look at that one table.
This makes its hardest job, what's called root scanning, unbelievably fast.
And there's another key design choice here: no compaction. A lot of garbage collectors like to move objects around in memory to keep things neat and tidy. protoCore's GC makes a promise. Once an object is created, it will never move. Its memory address is stable for its entire life.
This has two huge benefits. First, it makes it ridiculously easy and fast to integrate with other languages, like C++, because they can just hold a direct pointer to an object and not worry about it suddenly vanishing. And second, it makes performance way more predictable. The GC isn't going to suddenly pause everything just to shuffle gigabytes of memory around.
So there you have it, our 3 secrets: smarter objects, lock-free state, and a blazing fast GC. But the real genius of protoCore isn't just that these are 3 good ideas. It's that they are a single, unified architecture where each part makes the others even better. Let's just trace the connections, because this is beautiful. The smarter objects, they give us those fast data operations, but their efficiency also means there's less junk for the GC to clean up. The lock-free state, it gives us amazing concurrency, but it also enables that lightning-fast GC root scan we just talked about. And the blazing fast GC, it gives us predictable, low-latency performance, which in turn makes that fast C++ integration possible. See, it's a virtuous cycle.
And this whole elegant, synergistic architecture, it isn't just some cool theory on a whiteboard. It is the cold, hard, verifiable reason we see the performance numbers that we started with. So let's just look at them one last time. That 34x speedup in array operations, that's secret number 1, smarter objects and immutability. That 3x speedup in concurrent ops, you guessed it, that's secret number 2, lock-free state. And that incredible overall average of 19.83 times faster, that is the power of all 3 secrets working together in perfect harmony.
So the mystery is solved. The 20x speedup is real, and it's the direct result of a fundamentally different way of building software. And that leaves us with one final, pretty big thought. If just rethinking some core assumptions can lead to a 20x gain here, what other standard practices that we use every day are just waiting to be completely disrupted?